Myself Papa Vishwas, and I am from Indian Institute of Technology, Kharagpur, from Mechanical Engineering Department. And today I am going to present my paper titled by Improved Strength of Cylindrical Joint through Adhesive Tailoring. I used in the adhesive in step for piecewise functionally graded material to optimize our peak stress and improve the joint strength of the design. This is the 2D geometry of our model. In that figure 1 is 2D single adhesive joint, and this figure 2 is 2D bi-adhesive joint. The material I used for this our model is titanium shaft and titanium tube, and 3 adhesive I have used an ESP 110 and DSP 490 and epoxy adhesive. This model have been copied from M.A. Khan and S. Kumar paper, and this their project we are trying to improving. We're trying to implement that. Then in the figure, in the first figure, there is in the inner portion is solid homogeneous shaft of titanium, and the red one is adhesive, epoxy adhesive, and outer black portion is the titanium tube, hollow titanium tube. And in the second figure, you can see that there is bi-adhesive joint. Bi-adhesive joint is there. Inner one is titanium shaft, and outer one is titanium alloy tube. And there is 2 adhesive in piecewise functionally graded. The dimension is already given. The problem statement of our design, we want to reduce the peak stress at the overlapping joint and at the interface of the adhesive joint and the interface of the tube and adhesive, where the failure tendency is more due to peel and shear stress of in the adhesive. In that paper, I mainly focused on adhesive, and in next we will focus on adherent also through functionally graded material. Our main aim of our design is to calculate the overlapping length, and the critical length, optimum thickness, optimum chamfer parameter, and symmetric tailoring length, so that we can get a better strength joint, cylindrical joint, or we can improve our mechanical performance of joint. This type of problem statement is applicable to aerospace, automobile industry. Now comes to model our to model in FEM, abacus software. In our of our problem, I generally taken an axisymmetric model. Through the axisymmetric model, I have taken a axisymmetric boundary condition at the shaft center, and I have given the freely adhesive is free to move, and outer tube clamped in U2 direction. That is the boundary condition of our FE based model, which is done in abacus. And this the fee meshing I have done with bias and highly fine element I have used for adhesive, so that we can gain a better sharp result at the peak. So that we can get a accurate result in our numerical prediction. This in the earlier PPT, you have seen that there we have applied the 38.08 kilonewton load, and which can be assumed at a uniform stress of 100 MPa through Saint Venant principle, as we all know as a mechanical engineer. In our abacus joining, I use 4-noded biaxial quadratic element of 2 degree of freedom per node. And for adhesive, if it is rubbery material type, then we use CAX ARH element type for our adhesive only. And for our adherent, we use by 4-noded bilinear axisymmetric quadratic material, and we have use tie constant for connecting adhesive to adherent. Adhesive, I have used already shown the material which I have given, and that is titanium. Now to verify our 2D result to 3D model or 3D model, that is our 3D model. That is the figure 5 is 3D assembly structure machine, and the figure 6 is loading and boundary condition which I have applied to our 3D model. In total, I have used 2 million nearly. Hello, am I audible?
Yes, yes, you are audible. Please
Thank you, sir.
continue.
In total, I have used 2 million nodes and nearly 2 million element of in cubical structure element. Element name is general purpose linear brake element, which is linear hexagonal element, C3D8R of 3D stress family. Which I've got the result is like that. The stress that is for axisymmetric peel stress axisymmetric model result. This dotted one and this is solid one is from 3D model. This totally it matched totally, but there is a little bit difference at the peak just due to difference of node number. In 2D model, I have taken 1,000 node at the adhesive line along the adhesive, but in 3D model, due to restriction of our computer system in IIT Kharagpur, we just able to take 200 element, 200 node through the adhesive. That's why the little bit difference is there. We also mesh our result through with the parent paper, which is MA Khan and MA Khan paper. That is the little bit deviation. This figure 7 is our verification of 2D and 3D model. Now comes to result. The critical analysis, I have taken 5 length. One is 8.5 mm overlap length. That length means overlap length, and another 16.5, 36.5, and 515 element, and 15 mm and 65.5 mm. During the analysis, post-processing analysis, I have found that if we reduce the overlapping length, the peel stress and also shear stress huge in everywhere of the joint. So it's better to have a little bit larger length so that we can have a lower peak stress rate, so we can achieve a great mechanical performance through in our axial load with our axial load. And in the analysis from the figure, both two figure, we can easily find that critical length is we can assume the critical length in 50 mm in case of our model. Although the critical length is vary with boundary condition and loading condition also. And the main definition of the critical length is there is the length in such a way the middle portion of the adhesive is in the middle portion as well, shear stress will be approximately 0. That is the other definition of the critical length. And with if we increase the length overlapping length, that will also reduce the peel stress at the overlapping portion. So that is it is good to increase the overlapping length. I also analyze the thickness variation, how the stress affect with the thickness variation of adhesive joint. I have found that if we increase the adhesive thickness, then we can get a lower peak stress at the overlapping end. And it is also saturated after certain time, sometime. Like I have found that 0.6 is the best adhesive thickness for such kind of in our model. So in there, I have found that at the left portion only 6.14 MPa peel stress, and at the right portion, I also found that it's you can also see that in there the blue one is right, so 0.6, and the huge reduction of peel stress at a negative peel stress also, although it's negative peel stress, positive peel stress also a huge reduction we can achieve in our model. That is the analysis of thickness in our adhesive joint, tubular adhesive joint. And this result have this result just because of the less if we increase the thickness, will definitely increasing the volume of adhesive. So less stress concentration, energy density in the adhesive bond, that increasing that helps to reduce the peak stress. Now comes to symmetry tailoring, what we have done to reduce the inter.
Yeah, Papa, this was little short and little conclusion slide.
Yes, tell me again, sir. I'm not getting it. Hello.
Yeah, conclude the
Okay, sir.
topic.
Please give me two minutes. I will calculate. For the symmetric tailoring, we have found that we can reduce the peak stress at the wood side, and we can also gain some mechanical strength for our joint, tubular joint. You can easily see that we have reduction 45% at the left side and 61% at the right side. Now symmetry tailoring shear stress, in the shear stress also we have reduced 27% at the left end of the joint and 39% at the right end of the joint. Now coming to strength of the joint, the strength of the joint we have measured through stiffness. If we increase the compliance rate, definitely stiffness will reduce just because of compliance material in our model. So we have found that zero point 0.4 volume fraction of 0.4 is best for our highest performance in our model. So that is the stiffness diagram. And now the conclusion is this kind of model we can practically implement through 3D printing and additive manufacturing. And this type of mechanical joint also improve, also can eliminate the older conventional joint, so we can get a lighter structure that may be helpful in aeroplane industry, aerospace industry, automobile industry, which are high speed vehicle. And now all questions are invited. Now this is some reference I have taken. Das DD Das Anpothan paper of Article Professor, and